Good afternoon and welcome to Cheg's live Stoichiometry Hours. If this is your first time, we are so great to have you. And if you're coming back, thank you for joining once again. My name's Allison. I'm going to be the instructor for Cheg's Stoichiometry Office Hours tonight. I am a student at the University of Louisville. I'm studying chemical engineering. I have SLA'd and been a TA for chemistry, organic chemistry, nursing chemistry, and then I've done some private tutoring in chemistry and calculus. I love teaching, love chemistry, love math. So it is perfect that I'm teaching stoichiometry. The way these sessions are going to work is I encourage you to ask your own questions throughout this live stream. My goal is to help you with any questions that you need. So I have some prepared for us to start, but I really encourage you ask your own questions, and that way I can help you. You can kind of use this live stream as a personal tutor. So any questions you have, type those in the chat. Then as we do the questions I've prepared, I'm going to ask you to be actively engaged. So responding to different little questions I have or planning how to solve a problem we're going to solve. That way you can make sure you're learning new things, and then just practicing so that you can get those good grades, good study habits, everything that you need. But again, it is so great to have you, and let's get started. So I wanted to start with a kind of easy little warm-up question. Converting 174.85 centigrams to kilograms. If you have any ideas on how to solve this problem, now is the time I'm going to encourage you. Tell me, how would you start to solve this problem? You can say how you would solve it from end to finish, give me a step to how you would solve it, or give me any conversion factor you might need. And then bonus points, I always say bonus points if you can beat me to solving the answer. So bonus points if you can get the answer before me. But I'm going to give y'all 30 seconds. Tell me any clues, any hints you have to solving this problem. And again, any questions you have, feel free to ask. They could be about something I brought up or anything from your homework, something you went over in class. So I encourage you, ask those questions. Got about 15 more seconds. What is like one little step to solving this problem? 3, 2, 1. Okay, so I always like to start solving stoichiometry problems by making like a little map of how I'm going to get from the beginning to the end. The way I go about this is called the factor label method. I was taught this in my sophomore high school chemistry class, and it's been the best thing I've been taught regarding chemistry since. So basically, we always start with what we're given, and in this case, we are given 174.85 centigrams. If you didn't know what CG stands for, now you do. See, we're already learning stuff. And now we need to get to kilograms. This question is asking for kilograms, so we need to get from centigrams to kilograms. And to do that, we're going to need two different conversion factors. If you said that our first conversion factor is going to need to be centigrams to grams, you're absolutely correct. So that's going to be our first conversion factor. And then we want to end at kilograms. So then we're going to put grams on the bottom, kilograms on the top. Some questions I get when I set stuff up like this is, one, why do we go to grams? We go to grams because grams is called our base unit. Every single conversion in chemistry and like any other science that would have conversions is revolved around a base unit. So your base units are going to be grams, liters, meters. In this case, we're using grams. So we always have to go to our base unit before we convert to another type of that base unit, because every conversion revolves around that base unit. It's a kind of difficult concept to grab at first, but if you can realize you always have to go to your base unit, you're going to be on a really good track. Second question I always get is, why do I place the centigrams and grams in the order that I do? Why in this square is centigrams not on top? The reason for that is like some algebra. If you are familiar with algebra in any way, you know that if you put something on the top of a fraction and you put it on the bottom, if it's that same number, they cancel out. Same thing goes with units. If you have the unit on the top and the unit on the bottom, those are going to cancel out. Since we want to end our problem with kilograms, we want to cancel out all the units that aren't kilograms. So by setting up the problem like this, We cancel out centigrams and grams, and we end with kilograms. Now that we have that all set up, we are ready to add those numbers in and get our answer. So first, we need a conversion from grams to centigrams and grams to kilograms. If you know that conversion, now is your time to shine. Type that conversion in the chat. You have 30 seconds. What is the conversion from grams to centigrams and grams to kilograms? 30 seconds starts now. All right, 5, 4, 3, 2, 1. Okay, if you said 1 gram has 100 centigrams, you're absolutely correct. Great job. And then if you said 1 kilogram has 1,000 kilograms, that is correct as well. So if you got those right, you're doing good on your chemistry knowledge. You already have a great understanding, so great job on that. And now what we want to do is just solve this problem. So the reason I write it out like this is because now it's really easy for me to do the math. I just multiply across the top and divide it by everything on the bottom. So this is what I'm going to put into my calculator, 174.85 divided by 100 times 1,000. So I'm going to put that in my calculator. You have 30 seconds. Beat me to putting in that in your calculator and see if you can type the answer and go faster than me. All right, can you beat me to solving this problem? If you're just now joining and you still want to beat me, just put what I wrote on the right here in your calculator and type it before 15 seconds ends, and you will beat me to solving it. All right, 5, 4, 3, 2, 1. Okay, our answer is going to be 0.0017485. Now, I have a second challenge for y'all to this problem. I want you guys to write that in scientific notation. So you have, let's do 15 seconds. I think that we're well versed on scientific notation to be able to write this. In 15 seconds, your time starts now. What is 0.0017485 in scientific notation? All right, 5, 4, 3, 2, 1. If you said 1.7485 times 10 to the negative 3, you're absolutely correct. I'm not going to focus on how we got there tonight unless someone specifically needs help. So if you're wondering, how did I just come up with that number? I need to know scientific notation. Don't know how. How did you do that? Let me know in the chat, and I'd be happy to go over some more examples of scientific notation with you. But if not, we're just going to move on. If you're just now joining, it is so great to have you. My name is Allison. I am the host for Check's Stoichiometry Office Hours tonight. And throughout this live stream, I'm going to encourage you, ask any questions you have, anything from homework, anything you've went over in class. I'd love to answer that for you. Love to be like your personal tutor here. So just let me know and I'd be more than happy to solve it right now. But we're going to move on to our next warm-up question, which is converting 34 kilograms to moles of sulfur. So again, I'm going to give you all the opportunity. Let me know, how would you set up this problem? How would you solve it? What steps are we going to need? What conversions are we going to need? You have 30 seconds to tell me anything you can about this problem, starting now. All right, about 15 seconds. Anything you can gather from this problem where we're converting 34 kilograms to moles of sulfur, that S stands for sulfur, let me know. All right, so we're going to do the same thing basically that we did above. We're going to use our factor label method. So we start out with 34 kilograms because that's what the problem gives us right here, as you can see. And then we want to get to moles. So like I said again before, we have to go to that base unit. That base unit is the equivalent for everything. So we have to go to grams first. So we're going to go kilograms to grams. Again, put kilograms on the bottom to cancel out kilograms on the top and leave me with grams. And then we're going to want to go grams to moles because the problem is asking for moles. So if we just kind of show the algebra, our kilograms are going to cancel out and our grams are going to cancel out. We're just going to be left with moles, which is what the problem asks. So now we are going to plug in those conversion factors. If anyone can tell me the grams to moles, I'm going to give y'all about 30 seconds. Tell me, how are we going to find grams to moles? How do we do that? But while we're waiting, I think we all know by now the conversion from grams to kilograms. We know 1 kilogram is 1,000 grams. So if you have any questions on that, let me know. But I'm going to go ahead and put that there so we just have that number done. And if you said that grams to moles you find from the molar mass on the periodic table, you're absolutely correct. Great job. Virtual high fives for everyone. We are going to look at our periodic table, and if you find S on the periodic table, which stands for sulfur, you are going to see that it has a molar mass of 32.07 grams per mole. So 1 mole has 32.07 grams. That is all of the setup for that problem, and now we're actually just going to solve. So again, this is the factor label method. I can multiply everything across the top and then divide by the bottom. So in my calculator, I would put 34 times 1000 divided by 32.07. I'm going to give you guys 30 to 45 seconds. Put that in your calculator and let me know what the answer is. See if you can beat me to solving that problem. You've got 30 seconds starting now. See if you can beat me. I'll be so impressed. All right, about 15 more seconds. What is 34 times 1,000 divided by 32.07? 3, 2, 1. If you got 1,060 moles of sulfur, you're absolutely correct. I need to be better about writing my units, but those are the units for this problem. So 1,060, goodness, it's a tongue twister, moles of sulfur. That is our answer for that problem. If you're just now joining, it is so great to have you. I encourage you, ask any questions you have throughout this live stream. I would love to answer them for you. I can basically be your personal tutor or whatever you need on this live stream. Just type any questions you have in the chat and I would be more than happy to answer those for you. So it is so great to have you. For now, we're going to move on, though, to the next question until we get a question or something in. We want to know the short, long, and spin configuration of gold. I'm going to start us off by giving the long, and I think that's going to help with the spin configuration. So we'll do, and the short one. So we'll start with the long together, and then I will give y'all some time to do the short electron configuration and the spin configuration on your own. So, everyone, if you have a piece of paper of the periodic table or your iPad, I encourage you, now's the time, pull up that periodic table. We're going to need it for electron configurations. We want to find AU on the periodic table. If you're looking at that lower column in the middle, it's towards the right 3 rows down. So it's going to be AU, that stands for gold. And fun fact of the day, in Latin, gold is aurium, A-U-R-I-U-M, which is why it's AU on the periodic table. Then now you know a cool, fun chemistry fact, if you know everything else that I've been teaching. But we're going to look for that on the periodic table, and we are going to write the electron configuration. It's going to be a long one, so bear with me. But I figure if we can do the electron configuration for gold, we can do the electron configuration for anything. So we're going to start at the top left of the periodic table where hydrogen is. And that is our 1s orbital. It's our s column. So we're going to have 1s2. That 2 is because there's 2 elements in the s orbital, 2 electrons in the s orbital. We then go down a row, and you'll be at the 2s orbital. There's two of those, 2 electrons in the 2s orbital, which is represented by the 2 elements lithium and beryllium. Then we go all the way to the right, and we should be at boron, which is represented by B. And we have 2p6, 6 electrons, 6 elements. Go down a row all the way to the left. So you're reading left to right, going down a row, left to right, just like reading a book. We're at 3s2, then 3p6, then 4s2, and then it gets a little weird because we hit something that's not the s orbital and not the p orbital. That is called our d orbital. And it's really weird because the d orbitals go back one letter, or not a letter, one number. So that's going to be our 3d orbital. I don't know why they chose to go back one. It's something with energy levels. That's probably beyond the scope for this live stream, but it is 3d10. All 10 are electrons and elements are present. Then we go to the right. We'll hit Ga, which I don't know the name of that off the top of my head. Gallium, though. Learn something new. And you will hit your 4p6 orbital. All 6 electrons and elements are present. We haven't quite gotten to gold, so we're still counting those electrons. Then we go down the row again. So we're at Rb, which stands for rubidium. And we are at 5s2. We go to 4d10. And then we go to 5p6. We go down another row. We are at 6s2. Then we're at 4f14. That's a really weird one. 4f. So again, just like that d orbital, it's going to go down a number from the d orbitals. Don't know why, but it's like a little stair step. Something to do with energy levels. And then we're finally almost to that gold. We're in that d orbital that gold is present in. So we count. We have 1, 2, 3, 4, 5, 6, 7, 8. Au, gold, is the 8th electron, 8th element in that d orbital. So we put 5d8. And that big, long thing in green is our long electron configuration. If that made sense, great. Let me know by putting yes in the chat or something. If it's not making sense and you're like, why did you just say a lot of S, P, D, F, and random numbers? I have no clue what you're talking about. Let me know in the chat and we can go through it more slowly and better so that we can all get a better understanding. But now that we have that long electron configuration down, I'm going to give y'all 1 minute to figure out the short electron configuration of gold. Should be a whole lot easier, whole lot less writing. So you have 1 minute. Let me know the short electron configuration of gold, which is represented by Au. Bonus points if you can solve it before I start solving it. All right, about 40 more seconds. What is the short electron configuration of gold? All right, 30 seconds. It's your last few moments. What is that short electron configuration? I really encourage y'all to actively participate because that way you're going to get practice, you're going to learn things, and making mistakes when participating is how you learn. So any questions you have, any comments, or trying to beat me, I encourage you to participate. 5, 4, 3, 2, 1. All right, let's pull up that periodic table. We're going to do the short electron configuration. So let's zoom in so we can actually read what we're writing. Okay, the way short electron configurations work is we find the last noble gas on the periodic table. So the way you do that, you go up one row from your gold and all the way to the right, and that element is your last noble gas. So if I go up a row from Au, I'm at Ag, which is silver. Then I go all the way to the right and I get to xenon, which is Xe. So in these brackets, I'm going to put Xe, and that represents xenon. You can think of those brackets and that Xe is like a placeholder for everything you've wrote before that noble gas. And then we just write everything that comes after xenon. So If I go down a row, I'm going to be at 6s2, and then I'm going to be at 4f14, and then 5d8, and that is my short electron configuration. So that XE, just to like better visually represent it, that XE in brackets represents all of this, is what that represents. And then this is just the same as this right here. Okay, now you guys aren't going to like me here for a minute, but this is the way my teacher taught me, and it's honestly the only right way to learn spin configurations. We want to draw the spin configuration of gold. So it's going to be a long time, going to take a lot of writing, but it's such a great way to learn the rules of spin configurations and get that practice in. So we're going to solve this one together. So I'm going to put one line to represent my 1s orbital, and then I have two arrows represented by the 2, so 1 up, 1 down. Same with 2s, 2s2, 1 up, 1 down. So I'm going to cross them out as we complete them. And then we have the p orbital, which actually has 3 lines. The 3 lines represent 3 subshells. Each subshell can hold 2 electrons. There's your like chemistry terminology knowledge for the day, but this is 2p. We have 6 arrows represented by that 6 exponent. So we're going to go up, 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 down, down, down. If you're like, why are you just doing the up arrows first? That's because there's a rule. I think it's called the off-ball principle. Don't quote me on that, but there's a rule when doing electron configurations that says all the arrows have to be up or down first. You can't switch them until all have at least 1 arrow. So then we're going to go to 3s. Same as our 1s and 2s. 3p, same as our 2p. Up, 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 down, down, down. Then we're going to go to 4s, same as 1, 2, and 3s. So we have an up arrow, down arrow. And then we have 1, 2, 3, 4, 5 for 3d. 5 subshells represent 10 electrons because each subshell can hold 2 electrons. Up, 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 down, 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 down. All right, we're now at 3d10. And then we're going to go to 4p6. So I'm going to actually start writing it below. That way we don't run out of room, but we have 4p here. Up arrow, up arrow, up arrow, down arrow, down arrow, down arrow. 5s, up arrow, down arrow. 4d10, 1, 2, 3, 4, 5. Then lots of up arrows, lots of down arrows. We're almost there. Bear with me, guys. This is such great practice, though. 5p, 1, 2, 3, and then 6 arrows. Not fun in the moment, but I promise if you can do this, you're never going to miss a spin configuration question on a test. 6s, up, down. 4f14, okay, that's 7 electrons. That's 7 subshells, 14 electrons. So 1, 2, 3, 4, 5, 6, 7. Up, 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 up. Lots of ups and lots of downs. We're almost there. And we just now have to do that 5d8. So 1, 2, 3, 4, 5. 5d, and then 8 electrons. So this is when the up and down arrows are important. Up arrow, up arrow, up arrow, up arrow, up arrow, down arrow, down arrow, down arrow. And those last 2 don't get ups or downs. That is because of the off-ball principle. So they only have ups, no downs. That is the spin configuration for gold. Very long, very tedious, but great practice. And yeah, so that's the end of that problem. We have another electron configuration question. I figure since I showed you guys all of that, we should now like try to practice on our own. But if this isn't what you're currently going over in class, but you have another chemistry, another stoichiometry question that you want to ask instead, I'd be more than happy to solve it. And we wouldn't have to do any more electron configurations. So if you have any questions about what you're going over in class, topics you're currently talking about, currently needing to know, let me know. Type that in the chat of wherever you're streaming from, whether that be YouTube or Twitch. I'd be more than happy to answer for you. But for now, until we get a question, we're going to continue with the electron configurations. So for this one, we want short, long, and spin configurations of barium, which is represented by Ba. I'm going to have y'all start with the long configuration. You have 1 minute. Give me the long electron configuration of barium. So 1 minute starts now. Oh my goodness, I just realized how far in the periodic table barium really is. I'm not going to make you all do that since we just did gold. We are going to do calcium. Give me the electron configuration of calcium. Barium is crazy. Did not realize it was that far. But yeah, give me the electron configuration long of calcium. Yeah, 30. We'll give you 45 seconds. 30 seconds, long electron configuration of calcium. I'll circle it so we all know what we're doing. All right, 15 seconds, guys. Try to beat me. Start solving that long electron configuration of calcium. See if you can get it before I can. All right, 5, 4, 3, 2, 1. Okay, I'm at hydrogen. I start and I'm at 1s2. Both electrons are there. Go down a row at lithium and beryllium, 2s2. Go to the right. Now I'm at boron, so I'm at 2p6, all 6 of those elements, 6 electrons. Go down a row all the way to the left. I'm at sodium, which is Na, 3s2. All the way to the right, I'm at aluminum, which is 3p6. Down and back all the way to the left. So just like reading a book, I see calcium, it's in sight, and I just write 4s2. That's my long electron configuration. I know I went through that super, super quick. So if you have any questions about that, anything else, chemistry or stoichiometry related, let me know in the chat. I'd be more than happy to answer it for you. But now I'm going to give y'all 30 seconds to either give me the short electron configuration of calcium, or you can give me the noble gas that's before calcium. I'll let either be an acceptable answer, and you get a virtual high five if you answer either. So 30 seconds starts now. Got about 15 more seconds. All right. 5, 4, 3, 2, 1. Okay. If we have our periodic tables up, we will see that the noble gas before is Ar, which is argon. So for our short configuration, we are going to, I don't know why I'm writing configuration out, but we're going to put Ar in brackets and then everything after the Ar, which is just 4s2. The only orbitals between argon and calcium is that 4s orbital that has 2 electrons. It is 4s2. Now I'm going to give y'all 30 seconds for the spin configuration. I'm not going to ask you to figure out how to put those up and down spins in the chats, but I want you to tell me how many up spins there are and how many down spins there are going to be for this calcium spin configuration. So you've got about 20 seconds left now. What is that up? How many up and down spins are there going to be for calcium in its spin configuration? About 5 more seconds. 3, 2, 1. Okay, gonna start. It's gonna be extremely similar to the one that we did above. The reason I had you do such a long one is that when you do a long one, you can basically copy it for any shorter one to what you need. So just like above, we're gonna do 1s gets an up and down spin, 2s gets an up and down spin, and you can see that this matches up with what we did in the previous problem up here. Then we're going to do 2p, 1, 2, 3, 2p, up spin, up spin, up spin, down spin, down spin, down spin. 3s, up and down spin, 3p6, up, 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 down, 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 and then 4s. All right, and just like we see up here, this matches this exactly. So that's why I had y'all do that long one, that super long one, because you basically just solved every electron configuration ever, if you think about it that way. But now we are going to move on to our next problem. But if you have any questions, now's the time to ask them. So I encourage you, ask those questions. We're about halfway through. So that means you only have half of the time more to ask any questions you have. So please type those in the chat. But for now, we're going to move on to what's the limiting reactant. If I start with 18 grams of each, and it's barium nitrate and sodium chloride, which is also table salt. So you've got 45 seconds. I want you to tell me everything about the problem you know. So what's a limiting reactant? How do we solve limiting reactant problems? What steps are we going to need to take? You've got 45 seconds to let me know any of that information starting now. "30 seconds. "15. You guys got this. Anything you know about this problem, let me know. All right, 5, 4, 3, 2, 1. Okay, if you caught this first step, I'm going to be so impressed, but we need to balance the chemical equation. So to do that, we're going to basically cross multiply, if you think of it that way, the compounds. So barium is going to go with chlorine, and nitrate's going to go with sodium. So we cross those and we get BaCl2. There's a 2 under that chlorine because Ba has a charge of 2 plus. Then we're going to combine Na and NO3. So we get BaNO3 plus sodium chloride yields barium chloride plus sodium nitrate. That's the equation. Equation set. We do need to make sure that it's balanced. So this, I always forget to balance equations, and I swear every chemistry teacher I've had has tried to trick me with this. But we have one barium over here, one over here, 2 NOs over here. We only have one, so we're going to put a coefficient of 2. We go to the right, we have 1 Na over here, but 2 over here. So we're going to put a 2 coefficient. Then we have 2 Cls, 2 Cls. So we're good. Let's do one last check to make sure everything matches up. 1 barium, 2 nitrates, 2 nitrates, 2 sodiums, 2 sodiums, 2 chlorides, and 2 chlorides. So our equation is correctly balanced. If you have any questions on how I balance that, let me know and I can slow it down, or we can do some other practice. But for now, we're going to solve the limiting reactant part. So we need to start with 18 grams of each of our reactants. This should say 18 grams of each reactant. I forgot to put reactant in there, but we'll put that there so nobody gets confused. So we start with 18 grams of BaNO3 and 18 grams of NaCl. We need to get from grams of our reactant to moles of our product. The reason that is finding moles of our product is going to tell us what is the limiting reactant and what is the excess reactant, because limiting reactants, if you think about it, what a limiting reactant is it limits how much product can be made. So if we have a limiting reactant makes less product. So whatever creates less product is the limiting reactant. Hopefully that makes a little bit of sense. But now we are going to just solve and find our conversions that we need. So we always have to go to moles if we want to convert to moles of something else. And we can get those conversions from the balanced chemical equation. That's one of the reasons balancing equations is important. But we're going to go from grams to moles in both of them. And I'm just going to write this so we know what we're converting to. All right. And then we're going to choose one product to convert to. I'm just going to choose this BaCl2. It's the first one. I tend to always choose the first one. I'm going to go from moles of this to moles of BaCl2. Same at the bottom, moles of this to moles of BaCl2. So I now have the problem set up. I now, though, need to find the conversions that I'm going to need. So first, I'm going to need my grams to moles of BaNO32 and grams to moles of NaCl. So I am going to look at the periodic table for that information. So I'd go to BaNO32, pull up my periodic table. First, I would write out how much of each element I have. So 2 N's, 6 O's, and 2 Ba's. So I look at the periodic table, and I have my molar mass of barium is 137.33 grams per mole. I have just 1 mole. I don't know why I wrote 2, just 1 mole, guys. 1 mole of that, O is 16 grams per mole, and we have 6 moles, so times 6 moles. And then I have 2 grams per mole of, or I have 2 moles of N and 14.01 grams per mole. Then I'm just going to do those multiplication questions. So I get 28.02 grams plus 6 times 16 is 96 grams and 137.33. I'm going to add that all together in my calculator. Y'all add along with me and let me know when you solve it. You should get 261.35 grams. So I'm going to go back to my first top problem. I have 261.35 grams per mole is what I determined. So the 1 goes with the mole. Then I'm going to solve the exact same molar mass for the bottom. So find NaCl. Na is 22.99 grams per mole, only 1 mole, and Cl is 35.45, only 1 mole again. So I'm just going to add those together. I get 22.99 plus 35.45. We'll get 58.44 grams per mole. So I'm just going to plug that in. We have 1 mole there. And then I'm going to need those coefficients for moles to moles of BaCl2. And I just get those from the equation. So for BaNO3, I have a coefficient of 1, and BaCl2, I have a coefficient of 1. So it's just going to be 1 and 1. For NaCl, though, I have a coefficient of 2, and BaCl2 is 1. So now we have both of these problems set up. I'm going to give y'all about 1 minute and 30 seconds to solve this problem and tell me what the limiting reactant is. Your 1 minute and 30 seconds starts now. Try to beat me to solving the problem. All right, you've got about 1 more minute. Solve the problems. Tell me what the limiting reactant is. I'm going to start writing soon. All right, the first one, we should get 0.069 moles of BaCl2. For the bottom one, we should, actually, I'm going to wait a few more seconds to give y'all that bottom answer. Keep solving. Let me know what you get. All right, the bottom one, you should have got 0.154 moles of BaCl2. So it's kind of obvious now that we have that. What is the limiting reactant? What causes us to create less product? If you said BaNO3, you're correct, and that is because it creates less BaCl2. So 0.069 moles, less than 0.154. So barium nitrate is our limiting reactant. We did get a question from Schmaka on YouTube. Can you help me solve rational or radical equations? I'm in a high school, dual credit, and struggling. So I will solve like one or two of those, but I do encourage you join the algebra live streams from Chegg. That will be super helpful, and I'm sure they do that a lot, but we can do like one or two of them right now. So here's a quick example. This is also helpful in one of the future problems we're going to solve tonight. When we do ice tables and rate of reactions, you'll see a lot of radical solving. So it's great to know how to solve radicals for chemistry and any science you encounter. So let's solve the square root of 3x plus 1 equals 4. So if you have any ideas of how to solve this, let me know. But to start, I'll kind of work through it slowly. And so if we have any opinions on how to solve it, just type those in the chat. I'd be more than happy to help. But we want to get rid of that radical first. We want to get x alone and solve for x. So to get rid of radicals, we have to do the opposite. A radical finds the square root. We want to square the square root to get rid of the square root. So we square it and we get 3x plus 1 equals 4 squared. We can simplify that 4 squared. We know what 4 squared is, and if we don't, we can put it into a calculator. We get 3x plus 1 equals 16. Now what we want to do is subtract 1 because, again, we want to get that x alone. So we subtract 1 on both sides, and we get 3x equals 15. And last, we want to solve for x, so we divide by 3. Great job, Schmaka. Square is absolutely correct, so we get x equals 5. If you have any other more specific questions about radicals, we can solve those. But I have one more that we can kind of do, which is, this one's a little bit tougher, but again, it's going to help us solve those rate of reaction problems in chemistry. We want to do the square root of 5 plus x minus the square root of 4x plus 9 equals -2. So the way that we can solve this is by squaring everything. And so what we would do, or actually what we want to do first, is add that square root of 4x plus 9 to both sides. So we get the square root of 5 plus x equals square root of 4x plus 9 minus 2. Again, great practice for rate of reactions. So then we want to square it all. So we would cancel out the square root on the left side, and we get 5 plus x. But then on the right, we're going to need to use our algebra FOIL skills. So I'll write it out so we can all see, but we get 4x plus 9 minus 2 times 4x plus 9 minus 2. We just first inside, outside, last. So the square root of 4x plus 9 times the square root of 4x plus 9 equals 4x plus 9. And then we would do the minus 2 times the 4x plus 9, and we do that twice. So we'd have minus 4 times the square root of 4x plus 9. And then last, -2 times -2 is positive 4. So hopefully that is helping. And then we just want to solve for x. So it's going to get a little funky, but basically we're going to combine like terms. So we have 5 plus x equals 4x plus 13 minus 4 times 4x plus 9. Then let's do some combining like terms. We're going to subtract 4x and 13 on both sides. We're going to get -8 minus 3x equals -4, and then 4x plus 9 times the square root of 4x plus 9. Then we're going to divide by -4 on both sides. So we get 2 plus 3/4 x equals the square root of 4x plus 9. And then we're going to square it all again to get rid of that radical. So 2 times 2 is 4. 2 times 3/4 x is 6/4 x. And if we have 2 of those, it'd be 3x, and then 3/4 x times 3/4 x is 9/16 x squared, and we have that equal to 4x plus 9. And we're so close to solving. Again, great practice for rate of reactions. We're going to subtract 9 over here. So we get -5 and we'll also subtract 4x. I think we can do multiple subtractions in one step. So -5 minus x plus 9/16 x squared equals 0. And now, does anybody know how we would go about solving this now? So this is definitely something your teacher might require you to do when you get to the end of an ICE table, is use the quadratic formula to solve for x. So let's do a quick recap on the quadratic formula. It's x equals -b plus or minus the square root of b squared minus 4ac all over 2a. There's a song. Highly encourage you to learn it. Very good for helping you learn the quadratic formula. And now we're just ready to plug in all of those values. Great job, Schmaka. Quadratic formula is correct. So we want to do -b, which is going to be a -1, because that's an imaginary 1 for b, plus or minus the square root of b squared. So 1 times 1 squared is just 1, minus 4a. A is going to be 9/16. 4ac, and c is -5, all over 2a, so 2 times 9/16. And now we are ready to simplify. So we have 1 plus or minus the square root of 1 minus, I'm going to put 4 times 9/16 times -5 in my calculator. So 20 divided by 16 times 9. We get 1 plus 11.25, so that square root over 9/8. And then we're just going to keep on solving. So we'll solve for that radical. We're going to take the square root of 12.25. We'll get 1 plus or minus 3.5 over 9/8. And then we're so close. We're almost there. We're going to get 2 different answers that x could be. So x could be 1 plus 3.5 divided by 9 times 8, just because of the rules of fractions. And so that would be x equals 4, or we could do 1 minus 3.5, which is -2.5 times 8 over 9. And so in that case, it would be 8 times 2.5 divided by 9, which is -2.2. So hopefully that was a good review for radical equations. If you have any other questions, feel free to ask them. There's also the algebra office hours. But this way, that should be a negative. We have a little bit of a review going into ICE tables later in the live stream. It's always good to have a radical equation and quadratic formula review before doing ICE tables. Before we get to ICE tables, though, actually, let's go ahead and move on since we do have 12 minutes. So again, this is your last chance to ask any questions that you have. I encourage you to ask anything, things from homework, questions that you did in class live, any questions you have. I'd be more than happy to answer them for you. So let's go on to this ICE problem that will use our radical equations and quadratic formula. So what is the equilibrium concentration of the following if I start with 4 molarity of each? So I would do I, C, and E. I represents initial concentration, C represents change, and E represents equilibrium. I want to know equilibrium. So to do that, though, I have to solve for I, C, and E. We know that we start with 4 M's of N2 and O2 because it says each of the following, and this again should be reactants. I kept forgetting to write reactants when I wrote these questions, apparently. And then I'm getting ahead of myself because we need to balance this equation. It's not balanced. I'm going to give y'all 20 seconds, balance this equation. Let me know what the coefficients would be. About 10 more seconds. What are the coefficients of this balanced equation going to be? All right, 5, 4, 3, 2, 1. So the way I'd go about solving this is I have into here. I have O2 here, but I only have one O there. So I'm going to put the coefficient 2 there and then add another coefficient of 2 there. So then when I check, I have 4 N's on the left, 4 on the right, 2 O's on the left, 2 O's on the right. And now it is time to keep solving. I start with no product, so that's just going to be 0, and then I need the change. For the change, we do plus or minus depending on if that substance is being created or if it's being destroyed. And then we do change with the coefficient of the chemical reaction. So reactant is being destroyed or it's disappearing to create product. So we're going to use a minus sign. So minus 2 to represent that coefficient, minus 2x. Same with O2, it's being destroyed. It's a reactant. It's going to go away to create product. So we would do minus x because it has no coefficient, so no coefficient in our change. And then we're creating product. We have to create some sort of product or something. It's not going to stay at 0, so product's being created. We do plus 2x. And then we're going to do equilibrium, which just means we take all of these down and solve. So 4 minus 2x, 4 minus x, and then 2x. Then we need a k equation. For this, we're just going to say k equals 1. Your teacher will give you a k value, but for this, we're going to use k equals 1 just to keep calculations easy and nice and simple. Hopefully, fingers crossed. I write these questions never knowing what it's going to look like, and it's always crazy, I feel like. But good thing we got some radical practice, some quadratic formula practice to help us before. But now we need our k equation. K equals the concentration of products over the concentration of reactants. So k equals 2x over 4 minus 2x times 4 minus x. And then we are just going to solve. So we have 1 equals 2x over, we're going to FOIL like we did in that math problem that got us some practice. 4 times 4 is 16. 4 times negative 2x is negative 8x. Negative 2x times negative x is 2x squared. And then I think we're going to have a negative 4x from that 4 times negative x. And now we can just combine like terms in the denominator. So 1 equals 2x over negative 12x plus 2x squared plus 16. And now let's get everything to one side. So we would multiply everything on the bottom over. So we get negative 12x plus 2x squared plus 16 equals 2x. And then we want to get 0 on the right to use our quadratic formula. So subtract 2x on each side. We're going to get 2x squared minus 14x plus 16 equals 0. And now it should be looking familiar. We have it in the perfect setup for the quadratic formula. I'm going to erase this real quick so we just have some space to solve. Now we want to use the quadratic formula. So again, if you forgot that problem or that little formula, it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's plug those numbers in. X equals negative b, so negative 14, plus or minus the square root of b squared, so 14 squared, minus 4ac all over 2a. I'm going to give y'all 1 minute to start solving this quadratic formula, and I want you guys to try to beat me to solving the answer. Your 1 minute starts now. So try to beat me to solving that quadratic formula. All right, about 30 more seconds. Again, we want to try to solve for x in the quadratic formula. 15 seconds, guys. See if you can beat me to solving this. All right, 3, 2, 1. So we have negative times negative 14. We're going to get a positive 14 plus 14 squared, which is, if I can remember this, I think it's 196, but I'm going to put it in the calculator just to be sure. So 196 minus 4 times 2 times 16, get 128 over 2 times 2, which is 4. 14 plus or minus the square root of 196 minus 128. So the square root of 68 over 4. We're almost done. Square root of 68 is, let's see, what's that square root? 8.25. We'll round up. 14 plus or minus 8.25 over 4. I did a great job of creating these numbers because these are the easiest numbers I've created so far in any of these live streams. But now let's do 14. We can do 14 plus 8.25 divided by 4 or 14 minus 8.25 divided by 4. The way my teacher taught it is you can never have a negative equilibrium molarity. So you have to choose the one that will give you a positive equilibrium molarity. So we're going to need to choose the minus sign. If we do 14 plus 8.25 divided by 4, that's going to give us around 6 or something like that. And 6 as plugged in for x would give us a negative equilibrium concentration here and here. So we're going to choose that minus sign. We're going to plug that in. 14 minus 8.25 divided by 4. And we will get x equals 1.4375. If you didn't get that or you have any questions, let me know and we can go over in a little bit more detail. We have x equals 1.4375. And now our problem asks to find the equilibrium concentration of each of the following. So we want the equilibrium concentration of nitrogen, oxygen, and nitric oxide. So we are going to plug in that value of x, 1.4375 in for all of these. So for N2, we have 4 minus 2 times 1.4375. We're going to put that in the calculator. You've got about 20 seconds. Put that in the calculator. Try to beat me to solving it. About 10 more seconds. What is that answer? 5, 4, 3, 2, 1. You should have got 1.125 molarity. So that's your equilibrium concentration of N2. Then we want to do the same for O2. O2 is a little easier. It's just 4 minus the value of x that we got, which was 1.4375. So I'm going to put that into my calculator. 15 seconds. Try to beat me to solving it. This is a really easy one to put into your calculator. All right, 3, 2, 1. Should have got 2.5625 molarity. So that's the molarity of oxygen. And then we're going to want to do dinitrogen oxide. And that's just 2 times our value of x. So N2O is going to equal 2 times 1.4375. And you should get 2.875 molarity. All of these seem like normal molarities. They're all pretty nice numbers in my opinion. So we know that we correctly solved that problem. It was so great to have you guys join today. I encourage you, join again next week for more chemistry, more stoichiometry. Same time next week. There's also live office hours all week long at that QR code in the top left if you want to scan and figure out those and what else you can join. So great to have you. Hope to see you next week. Come with some questions. Bye, guys.